So what I'd like to do is talk a little bit about vector algebra, and particularly the geometric description of vectors and also the component description of vectors. So in E&M, we represent most physical quantities by two distinct classes of objects. And the first one are just real numbers, the scalars. These are objects that have quantity only. There's no direction associated with them. And as I say, they're normally real numbers. And here's a bunch of examples one could think of that are scalars. So it includes temperature, for example, light intensities, the mass of an object, charge, and densities of these two quantities are also scalars. One way to think of it is if you take the mass, which is a scalar, divided by volume, you're dividing one by the other, two scalars, that gives you a scalar. Well, the properties of scalars or real numbers include the commutative properties, and by that we mean this situation where if you're adding two scalars and go a plus b, you can reverse those and get the same answer. And the same goes for multiplication. The associative property has to do with taking these quantities and grouping them so that you'd have a scalar b plus c, so that's a scalar that you can add to a, or you can take a and b first and then add it to c. And so we associate as we go along here, and that is of course a reasonable property of addition of scalars. And multiplication is the same. So you can associate the quantities by just treating them like this, and so you'd have a times b times c equaling to this side here. The distributive property has to do with multiplying a quantity a times a sum. By distributing, we mean we can take a times b and then a times c. This actually could be a series of numbers, so you might have 200 of these things. You add them all up, multiply by a, or you can take them single term at a time, and so you'd have several hundred of these products, ab plus ac, and so on. The reflexive property is basically that if you take a equals b, you can turn that around, and so b is equal to a. So that's the way scalars work. Now vectors have both magnitude and direction. And so what are some examples of vectors? Well, there's force vector, displacement, velocity, acceleration, angular momentum, electric field, and magnetic field. And of course for us these two are very important. If you have 2 points in space and you take these points as P1 and P2, then if you go from this initial point to P2, you end up with a vector. It has the magnitude, which is the distance between those 2 points, and it has the direction given by this arrow that points from P1 to P2. If the vector is A, then we write that in many ways. Notice that this is bold-faced here. Here's A with an arrow, so this is not bold-faced. And we bold-faced A and put an arrow on it. Sometimes we just put a line under A, and we might do the same thing for the bold-face. All of these represent the same thing. Well, let's look at the old-fashioned way of adding vectors. So if you have vector A and vector B, and you want to add them together, you put the tail of B at the head of A, draw it, and then you can connect the tail of A to the head of B, and that will be the sum. So if you had B somewhere else, so over here, that's supposed to be B, you translate it over here and put it in the right position, and then close the triangle, and that will give you the addition. Does it matter what order they are? Well, you can see here I've taken B and then done the same thing, added A to B, and we get the same vector here. We can say then that we have commutation for the vector addition. If you were to take A minus B, then what you're doing is adding A to the vector minus B. And so here we have the vector A, here's B right here, we turn it around, minus B is headed off in this direction. So A plus a minus B will be equal to the vector minus B placed, see we've turned it around like that, and we've displaced it so that we have the head of A at the tail of minus B, and so now we have the difference in the two vectors. So let's go back here. So remember what we've done. This is the sum of the two vectors, the same two vectors. Here goes. This is the difference. You might say, well, this is bigger than this. Well, that's the way it goes. It has both directionality and angular dependence, and so for these two particular vectors, this is longer than the original sum. Vector multiplication by a scalar is very simple. If this is the vector A, and you multiply by the scalar little a, it just gets longer, it stays in the same direction. If you multiply by a negative number, so a is less than 0, it turns the vector around and it gets longer, and so you would have a vector that points in the opposite direction and has longer length. So if you have two vectors that you're adding together and you multiply by a scalar, then I think you can see that by increasing the length of a by a factor of little a, increasing the vector b times the scalar a will give you the situation where you can just add the two longer vectors. Just remember that if a is minus 1, then all you do is turn the vector a around, so b becomes minus a. Well, let's look at components and unit vectors in 2 dimensions. So we draw ourselves a xy coordinate system where if we take our right hand and curl our fingers from x into y, we have these oriented properly. And of course this is intuitively the way you would normally orient these axes. If we take vectors along these two axes with unit length, then we form the x unit vector and the y unit vector. And so these are the blue arrows that you see here. Throw in a vector a, and we form the components by projecting a onto the x-axis and the y-axis. The length of that projection of a on the x-axis is shown here. That's a sub x. And similarly, the projection of a onto the y-axis is given by a sub y. In terms of the length of this vector, which we symbolize by the vertical bars like this, is the absolute value, say, of a. It's really the magnitude of a. Then that will be equal to the letter a and will depend on the length of the vector a and the angle phi. So if you look at the triangles that you have here, you have basically the hypotenuse here and the opposite side here and the adjacent side here. And so by taking the sine and cosine of the angle, we can get then the component numerically a sub x and the y component numerically. So if we form the two vectors, which are the components of these two vectors with a unit vector in the correct direction, we have a sub x, x hat, and we have a sub y, y hat. If we add those two vectors, then we get the vector a. So here we go here. This is what we just said. That the a is equal to the vectorial combination of the components. In terms of words, it says that a is the x component of a times x hat, and then the y component of a, y hat. And we sometimes write that in terms of some sort of a bracket with ax, ay. So these are the vector components, but this notation is equivalent to this one right here. Let's take a position vector like we had before in 3 dimensions. So here's our point. It's positioned at the coordinates x, y, z. These coordinates are the projections of this vector r, the position vector r, onto the x, y, z coordinates. So for example right here, here's the point, here's the vector. If we project that onto the z-axis, then this quantity here would be r sub z, and that's what we call z. Likewise, we can project onto the x and y axes, and the simple way of doing that is to project down onto the xy plane and then do what we did in 2 dimensions. Just take the perpendicular to the y-axis, the perpendicular to the x-axis, and those will be the components. This will be the x component, this will be the y component. So again, if you take the vectors, the magnitude of the vector times its unit vector, so you take x times the unit vector I, and then likewise yj, zk, and add those three vectors up, then you're going to get the vector r. This is the equation for the vector r, the position vector in terms of x, y, z components, and so we have this sum, which is what you suspect. If you took this vector, and this vector, those are the projections onto the axes. Add those vectors up, you'll get the vector r. Again, we can put these in some sort of brackets, and these brackets here, the curly brackets, are those that are used in Mathematica to describe vectors. So if you write three numbers and these curly brackets, then you're defining a vector in 3 dimensions. Well, up here I show the description of these projections. Notice that these lines here represent 90-degree angles, and they're distorted, of course, by trying to draw this on a plane. Positions of the ends of those segments are these green lines here. So the arrows that give you the vectors along the coordinate axes are from the origin to those points given by the green lines. What about a unit vector in the direction of r? So you've got this system where you have unit vectors along the axes, but now you'd like to get something that's a unit vector along the r direction. So if you take r to be given as we've shown, or represent it in terms of just the magnitudes, then the unit vector, which is in the direction of r, will be equal to the vector r divided by its length. Let's go over that again. The unit vector in any direction is the vector that you're trying to find the unit vector of divided by its length, and that makes sense. If you do that, then you'll have the vector r divided by x squared plus y squared plus z squared. If you put back the vector r, which we wrote here, then you would have an expression that looks like this right here. If you examine that, then the unit vector, by the way, we sometimes call it this, sometimes we just put a hat on the vector r. So r hat is the unit vector in the direction of the r vector, and all we've done is taken r vector and divided by the magnitude of r. So just don't forget that the magnitude of r is equal to the scalar r, and if you want to relate it to the dot product, which we'll talk about a little bit later, the length of that vector is the square root of r dot r, and we'll understand this better in a moment. So here we go again. Here's the r hat vector, which is the unit vector along r. So we take the vector r and divide it by the magnitude of r, and that is equal to the square root of x squared plus y squared plus z squared square root. There's one thing that I want to make clear, is that these vectors can move around. They don't have to start at the origin. And that's what we did when we used the geometric argument for how to add vectors. We were able to move them around and put them where we wish. The vector is defined in terms of its magnitude and its direction, not from what point it starts at. So if we have a position vector pointing to this point P, and then draw the vector A of r from that point, we're fine. And so what we're defining then is the vector A starting at the point r. That's what this vector r represents. It comes up to this point P. So we have r in terms of its components defining the point, and then we have the vector A, which is starting at this point and is shown here. So if you had a bunch of points, let's say you had a bunch of points in space, and you had some vector which is a function of those positions, here's the origin right here, say, then you'd have A going off in various directions depending on what it represents. And these A's would depend on the position from where they start. And that's the beginning of a description of a vector field. So in terms of defining A, you can still talk about their components, where you realize that each component is a function of the position. You find the position that you're interested in, that's the vector r. You evaluate what would be called a vector function, in terms of its, say, 3 components, and then you're able to draw the vector capital A, which is a function of wherever it starts. So wherever this point P is determines what this vector A is, which means magnitude and direction. So A sub r we call a vector field if r spans some space that we're interested in. It can be all space, or it might just be a portion. Rarely do we draw in this vector r, even though we understand that the vector A depends on this vector r. Well, here's an example of a vector field. I used Mathematica to draw this. And so what I did was I took this function, which is a vector function, and I probably should put an arrow over it so that you know that it's a vector. And this is just the vector r hat, which is unit vector, divided by r. To do this in Mathematica, you have to get it into the form of a 3-dimensional vector. And so if you take r to be this quantity here, then r hat will be the x, y, z components divided by r. And so you can easily work this out. So that means our f, which is a function of x, y, z, will just be r hat over r. So I'm just writing this in symbolic form. And that will be equal to, here's r, right here, x plus y plus z. That's the vector r. If I then divide by the square root of x squared plus y squared plus z squared, then I will have r hat divided by r. So here's r hat, and here's r, and if we take that ratio, we'll get this quantity right here. Well, you can plot that using a function 3D, vector plot 3D. Here's the function, and we're just going to take x minus 2 to 2, y minus 2 to 2, z minus 2 to 2. So therefore you have this cube. Here are the answers by just doing these calculations. This right here represents r. This quantity here represents our function. So when you take this and center it at the origin, which is what happens when you go through these symmetric intervals, then here's where it originates, right here. This is the origin. And as you can see, the vectors are large, very close to the origin. That's why they look so big. And as you go out, they get smaller and smaller and smaller and smaller because of this 1 over r dependence. So the edges of these cubes are the axes, and because of the symmetry, you could choose any combination you wish, because, in other words, what you call x, y, z, because of the symmetry of the problem. Looking at this then, we have vectors everywhere. They have a function of position, in this case only on the distance from the origin. That's what we mean by an example of a vector field. Okay, so let's consider a 2-dimensional case where we have the origin right here, but suppose we have a vector field which depends on the position different than the origin. So this sort of is a 2-dimensional case of what I was talking about before, where we have a vector field that depends on position, and in this case we put the point of interest away from the origin. This is the same vector field plotted in 2 dimensions, where instead of using the origin, we use the point x0, y0. So what that means then is that the source point of this field is at this r prime, and that's equal to x0, y0, which is right here. The source point meaning that, for example, if this was like an electrostatic field, this is where you would put the charge, and then these are the field lines that come out of that charge. And clearly, they're not symmetric with respect to the origin at all. They're symmetric with where you put the charge. This vector field is not the the field of a point charge, but it's just the one we cooked up. What we do here is we define a new quantity, which is capital R, and this is the distance away from the source point. So now in terms of vectors, we have then a source point, which is this one up here, which we define in terms of this r prime. So the source point is at this x0, y0. The field point, where we're interested in finding out what the field looks like, is r. Forget about this. The field point is r equal to x, y. So it's this funny r, which is the important vector, because that gives us the relationship between wherever things are starting to where we're interested, and that's this funny r. Here it's a vector. Here it's a scalar because it represents the length of this funny vector. Well, what is that length? Well, it's going to be the field point x minus the x coordinate of the source point, and then the same for y. So the length of that vector, which is this funny vector here, is just equal to now x minus x0 squared plus y minus y0 squared, and then the square root. You can find the r hat of that vector by just taking the same thing we've done before. This is the x value of that vector, and then divide by the length, and then the y component divided by r. So here's our function then. This is the function that represents this field here as a function of x and y. So relative to the origin is what we're talking about. Well, that's going to be equal to r hat over r. This is a vector right here. This is a vector that represents then the value of the field given by r hat over r. So let's look at that. Here's r hat right here, and here's the length of r here. So when we put those two together, we get this expression here. If you now evaluate all these things, the first thing that comes out is the value of the function, which is exactly what I've shown you here. These, by the way, are comments, so we can put anything in here we want. This quantity here was found by taking r hat dividing by funny r. So then we plot it right here. We have to give x0, y0 some numbers, so I put it at 1, 1. And so then we plot it again from minus 2 to 2 for x and y. And this is a two-dimensional plot. Therefore, we only have two parameters, x and y. And the plot is what you see here. So the vectors, because this is like a 1 over r, this has big values near the point P, and then they fall off as you go farther and farther away, which is exactly like what we saw for the three-dimensional case. But now we have a two-dimensional case and an origin of field which is at a point different than 0. If we look then at the vector components and the unit vectors in 3D, we can look at them again, and you can see that if you have a vector A, you treat it just like that vector that we had for the position vector, but now this is a vector that is not the position vector. It may depend on position, but as we see here, we can take the components just like we did in 2 dimensions, write A like this, and we can write it in Mathematica notation if we just represent this as a set of components. This is a vector. This, of course, is a vector. The addition of vectors using components in 2D is very simple. You take the components of the two vectors, in this case A and B. The components will be defined in terms of the angles of the two vectors. So you have phi sub A, phi sub B, and you use the triangles that are defined by the vector and the components. And so you have the angles sine and cosine determined by the legs of the triangle and the hypotenuse. So you can write down those numbers here. Using those, we can get the actual components in terms of the lengths of A and the lengths of B. And remember, I'm drawing these away from the axes. In reality, we could have A x sitting here and B sub x along the axis. It doesn't matter. We can put them up here or down here. The length of B sub x is shown here. The length of A sub x is shown here. So what do? When we add them, we add the component. So here's A sub x, and then I have shifted B sub x up here, so here's B sub x. Adding those two together will give us the x component of the sum. So that's ax plus bx. We take B sub y and we take A sub y and we stick them on top of each other. And so you can see that you have ay plus by. That's the yth component of the sum. And so if you do that, then this is where you end up for the sum of those, and so there you have the vector a plus b in terms of the components. If we were to take the sum of a plus b, you can see that it also comes up to the same point. So this is the geometric addition of the two vectors. This is the vector addition using the components, and they give you the same result. So let's just look at that again. Here's the geometric vector b that we've taken and translated, so arrow to tip, and that gives us the same result for the sum. Well, let's go back to these unit vectors. The Cartesian unit vectors, and here I've written them as x hat, y hat, z hat, it could be I, j, k, form a basis for a three-dimensional vector space. And we can write any vector A that's in that space as a sum of components with unit vectors x, y, z. Because you can do that, that's what you mean by a basis. You can also use cylindrical coordinates that have different unit vectors, s, v hat, z hat. You can use spherical coordinates that has two angles, theta hat, v hat, and the unit vector r. We generally use these two when you have symmetry that corresponds to those two systems. If you have a cylindrical symmetry, you use this vector system, cylindrical coordinates, and then if you have spherical symmetry, you use this one. There are other unit vectors. Sometimes we write them in terms of little e, and these are specific to the chosen coordinate systems. There's many other coordinate systems besides Cartesian, cylindrical, and spherical, and you asked for it. Here's a bunch that are listed at the Wolfram website. We will concentrate on using these three. The only other issue about notation is this idea of representing them in different forms. You can have column vectors, you can have row vectors, and then this is the notation that I showed you before. The scalar multiplication, if this is a vector A, you multiply each component by k, so the vector ka would be given by this expression here. If A is not equal to the 0 vector and k equals 0, then the product will give you the 0 vector. We sometimes just call this O tilde for the 0 vector. And remember what the 0 vector is just all zeros. So all the components are 0. So here's A again in terms of components. Let's say that we have a vector where not all of these A sub i's are 0. Then multiplying by k, if you have k equal to 0, then the right-hand side will be the 0 vector. If you have 0 times A, you'll always get the 0 vector with or without the fact that this is a non-zero vector. I won't go through this in detail because I just want to show you that when you define vector spaces, you define the operations between the vectors. And so there's some operation that you would call addition, and there's some operation which you would call times. And these are vector addition and scalar multiplication. All I want to show you is that things that we have said already, that if you have a vector u and v, and they're in v, then the sum has to be in the vector space v. And then you have the commutative law, you have the associative law, you have the zero vector, which we've looked at already, and you have the inverses, additive inverses. So if you have each vector v in v, the equation v plus x equals the zero vector, you can then turn that around. X plus v is the zero vector. These will have a solution x in v that's called the additive inverse of v. In other words, it would be minus v. These are picayune results, but they make up a vector space. Other properties have to do with operation star or multiplication, which is scalar multiplication. I encourage you to stop the lecture and just take a look at some of these. You can see that it distributes. You can see that it has a law that allows you to add the scalars times v and distribute those in this way. And then there's an associative law. And then finally there's the existence of a unit vector. All of these things occur naturally in the Cartesian rectangular system, but they do fit into what is called the vector space. Let's look at these notations again. Here's A written like this. Here's B like this. If we take A plus B to get a vector C, that's written as a vector. Here's the sum of these components. So if you want to take this vector and add, we've already shown that you can take the sum of the components and that will give you the new vector. The same goes for multiplication, which we've already written down. The k distributes through the vector a.